Wow. Hey, this is Coffee Compiler Club, and anything to do with compilers and language runtimes and implementations and typing systems and nil and not the nil and what to do with GC and exceptions and everything else, all fair game. I don't have a set agenda. You're being videoed. The video shows up on YouTube. Oh, and here's yet another new person. Shows up on YouTube generally within a couple hours to a day. And we have several new people, so I'm going to pick on them to have them intro themselves. Derek, why don't you, there you are, why don't you start? I'll pick you as the initial victim, so like 30 seconds or less kind of thing.
Okay. I'm a co-founder of a company that we make AI chips. And we've been working for a while on a compiler, sort of internally. I decided about a year ago that this is an important problem, so I started studying, and recently decided to build a compiler completely from scratch for us and see what I can achieve.
Cool.
And it's going very well.
Oh, excellent. Yeah, I did, compilers for custom hardware chips, in a galaxy far, far away for quite a few times.
I have a lot of questions.
Yeah, I'm sure. So this is a big job for a startup doing hardware.
I have a working compiler. I have it working. Yeah, it's fun. I mean, I didn't call in to just brag about it, but I'm very pleased. There's a long ways to go, though.
Let me rotate around the other new person, and then maybe we can come back around. You can tell us what you're doing for your compiler.
Love to.
Federico, do you want to say something about 30 seconds while you're here?
Me?
Yeah.
I'm just a regular developer. I had an interest in languages development because I think the hardware out there is severely underutilized, and I can think of very aggressive optimizations if you make some fundamental changes to the language. All of these design decisions are it's just because I'm poor, so I think we could reuse old technology if there wasn't that much bloat on the software. That's all there's to it. I am a cheap guy, and that's it.
Problem. Where are you located, time zone wise? Can you hear me? No. Okay, where are you located?
Yes, I can hear you. I can hear you. We are on a near time zone. I got you.
Totally broke up. Your audio is really bad.
Yes. So did you get my introduction?
Yes, and I did not get.
Okay, so all right. My time zone. It's 2 p.m. here right now.
Okay.
Yeah. GMT -3. That's my time zone.
Okay. You're in South America then.
Yeah.
South America, Federico?
South America or Eastern Canada?
South America, Brazil.
Yeah, okay.
Brazil.
A city in the middle of nowhere.
Yeah.
I hope your download speeds are better than your upload speeds, or this is going to be a really hard conversation to follow.
Yeah. No, I can.
Totally lost him.
Okay.
No, totally lost him. Cut your video.
To piggyback on what he was saying, though, there was a time when I advocated that developers shouldn't have top-of-the-line hardware to force us into writing more optimal code, but I no longer feel that way because I want a fast computer.
So,
what do you mean?
So Federico, kill your video because that'll cut your upload bandwidth, and we'll all hear you maybe better. Okay, cool.
Uh,
I was going to.
I know that just a reply to one comment about I also had that opinion that developers should not have the latest hardware. I have not changed my mind on that because I think we are trusting the hardware too much. You might not have ever been hacked, but
Oh, I lost you. All right. I'm gonna moderate for a second. Let somebody else have a turn here. But Federico, you can have another turn in a little bit here. But your audio just cut out as well.
Yeah, my connection is quite bad.
Yeah, I'm sorry, and it is. But let's
okay.
go here. So, Matthew Zarnik. I haven't heard from you in a long time.
Charnik. Yep.
What have you been up to?
Charnik, like check. So I'm working with Federico actually. We're working on creating a new language, trying to simplify high performance programming. How do you get it?
Scientific, big arrays, big data.
It's kind of general purpose. Just back end and mobile. And, at the moment we're focused on desktop, and that's our first one, but we'll go from there.
Yeah, sounds good. I mean, that's what I'm doing with AA as well, basically.
Mm-hmm.
Mobile, desktop, and anything with performance where the CPU actually matters as opposed to getting rid of other software layer bloats. Okay, let me roll back around and pick up, I'm gonna say Derek, and then I'll come back around to Matt and Federico, and that's as much agenda as I ever do.
Okay.
Derek?
Yeah. So I can talk about kind of what I've consumed in terms of learning to get started. And,
yeah, please do.
So basically, there were two main influences on the work that I'm doing. The first is, well, it's hard to order them, but anyway, the IU compiler course, which went online in 2020. I don't know if you guys know of it, but it uses this Nanopass technique.
No. I remember the Nanopass. It was fine. No.
Yeah. So the Nanopass compiler, I don't know if I'm sure you've looked at it. It's pretty confusing. It's like a lot of macros. But it seems like there's some good ideas in there.
Let me pull up the links for when I talk about the IR that's in Java forever and a day. I have them all the time, damn it, and people keep asking. I'll go find them.
So there was that. So I did that course, and it's nice because you get a working compiler like basically on day 2. On the first day you start coding, and then you start building it iteratively on it, and you build a register allocator, and it seems like it, and I was trying to read about register allocators, and it seems like the one that they sort of guide you through is not bad. So that, and then there's another book that came out last year called Software Design for Flexibility. It's by Jerry Sussman. I don't know if you guys know him. He's the SICP guy. And so his big obsession is computer algebra systems. And those things have heavy duty, very powerful pattern matching in them, especially the way that he builds them. And so he basically lays out the design for the architecture for that pattern matching system in this book. And so I did that. I built the stuff from that book, and then I basically spent a long time scratching my head over how the Nanopass compiler is actually designed and what it's actually doing inside all of those enormous macros. And I basically adopted the dialects idea and some way of doing guided descent through trees from that, but threw away everything else. And then I implemented a bunch of their passes using my thing. It came out much cleaner without macros. And oh, I should mention I'm doing everything in Clojure. And
do you have
so
an influence?
I see Cliff like, oh my God.
No, it's personal choice. It's the every language has it.
I'm not judging here. First compiler, sure.
Have you been influenced by other languages in some ways?
Well, so the language that I'm building is actually I'm compiling from syntactic Python through. I compile Python to Clojure, and then from Clojure to directly to through a bunch of passes to our bytecode. So we have our own chip, it's our own processor, it's our own bytecode.
Python to Clojure transpiler, source to source?
Yeah.
And your
so
bytecode, the chip
Python and Clojure don't think that similarly.
It's true, but I'm not trying to compile the entire language. I'm trying to compile everything that you would want to do on our chip. And our chip, what we program is it's a controller that drives an array, and the array is doesn't really look like a conventional CPU, but the controller is basically a RISC kind of a RISC core, and so you basically care about loops, function calls, conditionals, and integer math. That's pretty much all you care about in the controller.
Yeah.
But that stuff translates pretty easily.
Are you running? Is the controller running a bytecode interpreter, or you go to machine code eventually?
I go to machine code. I have a simulator that I wrote, so I can sort of I can compile programs and run them in my unit tests. I haven't gotten to the point of actually running. I only started this a month ago, so I haven't gotten to the point of running this on the chip yet. But
you have silicon.
But basically,
we have silicon.
Nice.
Your chip optimizes for some SIMD style.
Yeah, it's like a GPU.
Yeah, it's not like a GPU. It's the architectures, we call it at memory, and there's a bunch of interesting details in terms of how you run it. But basically, normally a SIMD, you're flowing pretty easily in a CPU between the SIMD and regular instructions, and there's not really a very hard boundary. If you can keep things lined up nicely, you're going to do better. But you can line things up and then run SIMD instructions. In our system, you don't want the data to go through the controller ever. So, yeah, but we're doing neural nets, so the workloads are complex but simple.
Is the language center about for style loop coding, while loops, for loops? Does it have some kind of dedicated primitives to help it work it more easily?
Yeah, so right now I'm thinking in terms of dedicated primitives. So we have a lot of mechanisms that need to be run. And so I'm not trying to, solve everything at once. And I don't think it's possible to pretend that the workload in the array is the same as a conventional sort of one-dimensional CPU workload. Because we're very two-dimensional.
Yeah, right. Yeah. I done a startup doing, machine learning and big data, and we did neural nets for sure. But we're doing on x86 in Java, but we spent a lot of time making sure we treated the data set right, because it was well, your time went.
Yeah. So, and I have, I have the sort of, I'm starting with vanilla everything, as in terms of getting the baseline stuff working. But I have a bunch of ideas, So, for example, I'm wondering if anybody has ever done like compressed register allocator, because like we've got a 16 register machine, but we almost always deal with 8-bit ints. So why don't I put 4 values in every register?
That's not compressed registers, that's packed.
Packed. Okay, well, there you go. That's
and of course,
problem.
x86 being what it was and the history of it, you had 8-bit registers, then you had 16-bit registers, and then you had 32-bit registers, and then you had 64-bit registers, and all on people, when the new registers showed up, packed double the prior size in them or not. And it was a way to trade off having too few registers for having more cycles burned to avoid just spilling and loading and storing.
So it's not necessarily more cycles burned, but more instructions.
Yeah,
because it might still be less it might still be less cycles.
Yes, because the loads and stores were more expensive according to whatever your hardware the choice was. So it was, register packing and register pairs was the other common word you would look for.
Okay.
And I know I implemented register pair allocation in the hotspot JIT, right? So I mean, I did it many times, but it's definitely been in the hotspot JIT forever. It got turned off when everyone finally settled on 64. But while it was 16 or 32 bits, we totally ran pack registers or pairs.
Yeah. Okay. Yeah, because I was thinking that you basically just set up your interference so that there's a sort of tree of interference that can happen.
Well, you're doing a graph coloring register allocator, or are you doing a linear?
Yeah. Move bias graph coloring allocator.
Yeah. So I'm a big graph coloring fan. Yeah, you have to screw around with your interference graph to get people to color right. And there's some other things that, we can go down the register allocation rat hole for a long time. That's a big, deep rat hole.
The problem is actually that you don't know it's going to be a long time, but when you go down the rat hole, you might never come out because it's not provably completable.
Yeah.
You might, but I'm good at giving up on things, so.
Does your new language has a name?
Yeah, well, temporary name, it's just Magic.
Magic, okay.
And can you say the company name?
It's Untether AI.
Untether AI. Yeah, I've seen the name roll around. Fine.
Okay. Hey, that's good.
So. Sorry, go ahead.
No. So So I'm doing this sort of skunkworks project, and there's a whole team of people working on, proper compilers and whatnot. But I thought, hey, I'm just going to do everything, anything that I can think of, if I can keep my code base simple and I can sort of experiment and move things.
All right, so now the old man's going to tell you some advice, and then I'm going to pick on somebody else for a minute.
Yeah.
Go look at my stupid videos I put in the chat, the Google Docs links, which are 30 minutes of a month ago, Coffee Club, where I did, hey, here's my IR. It's not the Nanopass compiler.
Yeah.
It looks like Theodore threw something in chat, maybe. Yeah, the Google Docs, thanks. And that's an IR that is well suited for optimizing sort of generic junk code that floats around. It's not super awesome for doing loops per se, although it doesn't have any worse than anyone else for doing loops. But if you're all about pushing the main work loops onto the chip, then you don't care about that. As for generic complicated things getting generically optimized, it does a great job. And I claim it's very easy to understand, but your mileage may vary. And and as for having a skunkworks project doing register allocation, we're already talking register pairs. I claim that that is in fact a rat hole. You can go a long ways down it. When all other optimizations are running well, the register allocator keeps coming up with an extra 5%, an extra 5%, an extra 5% as you keep pouring more and more time down that rat hole. So it seems like a valuable rat hole after a while, but it's a deep one. So I would watch your time spent on that rat hole and decide that maybe it's time to postpone and come back around after you've visited some other things that you might find more exciting. Like moving loop invariant array math out of other loops is probably a bigger win than anything you'll get out of the register allocator.
Okay.
Just throwing that out there.
But from the architecture, it seems like the big win is making sure your arrays got tiled properly so they fit on the chip.
They have to fit on the chip. Yes. Yeah. Yes.
So that's like that's above the scale of the control. Like one controller controls one array, and then you have a bunch of controllers. So I'm currently dealing with the one controller.
Okay. There is a theory, which I think Aaron's totally right here. There's a theory that says somewhere you have a unified compiler that understands the sea of chips that you have and tiles accordingly. Someone should pay attention to that. But then you can assume, on the one chip you believe it fits. But you still might have loop invariant chunks on a chip that are different from chip to chip according to how the tiles are breaking out.
Yeah, absolutely. So my theory is that you want some powerful tool to build that higher level compiler. And so I'm sort of saying, okay, let me build something that I can write kernels for a given bank fast, like in terms of programmer time, not necessarily the maximum optimality, right? So, maybe not worry about fancy register allocators right away, but, get it working, get it expressive, and start throwing ideas at it, and then start building up layers, right? So because you're absolutely right, like that's the key. It's one of the big drivers.
So let me caution you about the layers approach, which everyone has to in the end, but there's a deal there that's not obvious when you go in, and that's the layers interact badly often, such that if you tweak something at a high level to fix some issue somewhere else, some unrelated issues at the low level will now blow up on you and produce so much worse that you'll net loser. And the interactions between layers make it difficult to fiddle back and forth between them such that everyone wins in the end. So my general philosophy for the straight up, CPU only, you have a homogeneous, a heterogeneous technology running around here. So in a homogeneous CPU world, I got away from Nanopass and layers and instead went to this sea of nodes things where essentially I had one flat layer. And that got rid of a whole lot of problems where the layers interact badly, and you played whack-a-mole while you fixed something in one layer and something broke up in the other layer and you made no forward progress. You fixed that guy and the first layer blew up, and back and forth and back and forth. Worked out better in that sense.
Yeah.
I'm not doing a heterogeneous system right now, so I don't know. You might have a different.
Yeah. I was thinking that going between IR types might be good. So, I watched your Sea of Nodes talk a while ago, and actually, I'm pretty sure that the rule simplifier that I have does a very, very similar thing. And because the way you describe iteratively sort of, so I don't have a work list. I don't care that much about my total speed of the compiler right now.
Right. You'll hit quadratic to exponential. You'll go exponential if you don't eventually go to the work list version.
Yeah. So when performance issues hit me, then I fix them. But right now I haven't. So one of the things is that I've got a very small program memory space. If you try and compile a Linux kernel, you can try, but you're not going to get much loaded.
Right. Gotcha. So all your programs must be small.
Yeah. So then I'm thinking maybe the exponential stuff I can just ignore, maybe, except for the really, when you get high exponents.
It could be. I don't know.
Yeah, that's right. I don't know either, and it's easy to do what I'm doing, and then when I get hit, then I go and fix.
So in the land of H2O, big data, machine learning startup, we would build models and then we would deploy models. And the deploy models were machine generated code that was expressed as the model guts. And machine generated code tends to hit the same thing over and over and over and over again. So for instance, you may have a random forest might give you nested ifs that are 200 levels deep. And then people who did tree walks on nested ifs without doing a visit bit would go exponential to a power of 200 instead of 3 or 4 like a human might write. And suddenly what would be a few seconds became a few hours. And, you had like, oops. just saying, if you head down that path, machine generated code is all happy to hurt you in ways that human generated code does not.
Oh yeah, I know. That's okay. I'm willing to try to torment myself and see if I can find the nasty cases.
Sounds good. Do you want to throw out any more comments, and then I want to pivot just so I can get time on the other you folks here.
Yeah. I can keep on going as long as people want, because I have a whole list of topics that I wouldn't mind talking about, but it doesn't have to be all this time, and I want to share time. So
hey, Derek,
I'll shut up for a bit. Yeah.
So Derek, one of the guys who sometimes is on here is Max Bernstein. I put a link in the Google Doc, and he's working at I don't know if he tells people where he's working, but he's working at a big company doing a Python runtime compiler.
It doesn't rhyme with base look or anything like that. But he's
never heard of it
today, although I don't see him, and he had progress made on his Python jet that he was going to talk about. So we'll see.
Yeah.
All right. I'm gonna.
So I shot him a note with your name, so hopefully he can get in touch with you.
So Matthew, Charnick, I'm gonna pick on you because I lost the other guy.
Yeah, Frederico dropped off. He was having too many internet issues. So
yes, it sounded like he was having internet issues. So what can you talk about what you're doing?
Yeah, so a little bit. So I got into it with the idea of basically how to make a more productive language. That was my initial goal. Was I wanted to figure out what makes it what improves productivity for programmers when they're working with your language, and what slows them down and that kind of thing. And then was inspired by Rust to kind of try to, instead of using a garbage collector, a typical garbage collector, to create something that's more based on Rust, but users don't have to think about all that ownership.
What's the language called? If it had
Flogram. There is a website out there. It's pretty
Please
old,
share a link. I will put a link. Okay. In the chat or in the docs, I will share.
Flogram.net?
.dev.
.dev. Too many Flograms.
Yeah.
Yeah, okay. Found it.
So we're trying to focus kind of primarily on the how do you make a very productive language and still leave it running fast, basically create a high level and low level language where you can code in the high level language, but if you need performance, you can drop down into low level language, and it's kind of the same language, just a little extra keywords there that you need to throw in, basically.
And that's my goals for AA as well, but I'm not hugely far along either. I went down the typing theory rat hole, which is very unrelated to anything.
No, I know that one.
Excellent.
Yes.
So you have that website's pretty bare. Do you have any other links, or you have any code examples, or you're like, well,
Frederico is working on them at the moment on kind of. Oh, we have a big Google Doc, but it's really old, and so he's working on kind of coming up with the newest language spec based on all these conversations we've had.
Do you have a GitHub link with a README, or?
Not at the moment. At the moment, we've been keeping
like
everything.
State of my docs. What the hell?
So yeah,
looking over the bullets though, I'm curious if you can tell us about automatic threading and automatic async.
Yeah. So yeah, that was some of the goal on the whole productivity front. Is like, why, you know, what can you automate and have the computer do for you that instead of having the programmer have to do it. So on the automatic threading, yeah, it's one of those things where we haven't been talking about a lot of stuff publicly, and we wanted to kind of wait, kind of on anything high performance until we're like ready with that initial version. At the same time, it's good to talk about.
So you got some thinking you're not ready to share, or you're worried about
some of it. Yeah, I guess I mean a little bit worried on the whole. You know, what if someone runs away with it? And,
all right, fine.
But
I
can talk about it in high level. I'm just
someone's going to steal my tech.
Yeah, exactly. And like, I mean,
So you can share the main ideas, not the specific features.
Yeah. Yeah, so that's kind of what I'm thinking, because there are a lot of little gotchas. But the basic idea is that we look at functions, we determine what is the what is the cost to thread them versus the cost to not thread them, and then because we're a more functional language, it's easier to do that threading.
You said cost of a function. How do you measure the cost of a function?
Cost of a function to thread a function. So there's a certain price to thread a function, which is the cost of spawning a thread, or the thread grabbing a thread from the thread pool.
Right.
Versus the cost of just running it in the same thread.
Right. I'm asking, how do you judge the cost of running some straight line piece of code such that you can make a measurement relative to the spawn cost?
Basically, it's the cost of the functions inside the code. So it's kind of built up all the way from the simplest ones all the way to the.
So what do you do with loops with unknown extent?
We have a for like for loops, for example, you can kind of figure out the cost. For while loops, well,
I'm confused why for loops you can figure out a cost for.
Because it's so some of the times you can, sometimes you can't. Basically, we let the coder give us an estimate and say we estimate it'll take be able to run this many times. So it's a question of, you know,
so there's an annotation by the programmer.
Yes.
On each loop saying, I think this guy averages 10.
Yes. So we can kind of estimate for them in some cases, especially if it's known how big it is, or we can kind of
I mean, the usual story is the iteration count passed in as an unknown value.
Yes.
I missed,
but yes.
I missed one of the details. Is this a, you know, dynamically compiled language or a statically compiled language? As in, is it all upfront compilation where you have to figure this all out before emitting any code, or is it something?
Yes. There may be some runtime checks here and there, but for the majority of the case, it's all compiled up front.
Okay, I see.
Like the guy doing neural nets, so Derek there, like he has a reasonable chance to rejit small code for a small chip, where at the time that he jits the code, he knows exactly the number for the loop trip counts.
Mm-hmm.
You might get that at that late stage. You might actually have a raw number. It's 17.
Yep.
And, you know,
yeah. We can. Yeah. That can be done too. At the time that the loop is about to run, you can know how many. You know, most of the time for for loops, know how many times it's going to run. But sometimes that's a little bit too late to know because you can't just
You don't get it all the time.
You can't just spawn hundreds of threads, or else that's going to slow everything down. So
right. Well, then there's a question of like, do a runtime cost estimate, you carry history of how long this loop's iterated in the past, or I'm just asking, like, what is your plan for the general case of I don't know shit, but there's clearly a lot of work to be done. When do I spawn and when do I not? And if you're not ready, just say I'm not ready. I haven't got that far.
Yeah, I mean it's mostly right now it's mostly just we kind of estimate it using user estimates and
I that annotations, that was interesting.
Yeah, exactly. So
okay.
And yes, we might do some of that, but as much as possible, I'd like to do it at compile time.
Well, one of the great learnings of Hotspot was a whole lot of dynamic everything's. So JIT time or compile time alternates with the runtime, and then you can mix some of the runtime info for the next round of JITting, and that was very productive. So I didn't do it for trip counts directly, except there was a general profiling that went on, and so when it came to a loop of while loop or for with an unknown iteration, whatever, I did have profile that gave me history of what it used to do for the first however many iterations I ran before I JITted, and then you lived with whatever you got at that point.
Yeah, it's a good idea. Yeah, kind of like
it's a lot of work, no question.
Yeah.
Profile directed feedback on your JITted code has an interesting amount of performance gains, but also an interesting amount of work. You know, there's cherry picking where you work a little bit of work and you get a little bit of gain, and there's watermelon picking, which you should always do. You find these giant watermelons, you grab them and run, and then there's things where you worked really hard and you got a good gain, but you worked really hard to get the good gain. I don't know what you want to call those kind of pickings, but we did all of the above, and I would claim the profile that falls into that category. It was a lot of work and it was an interesting gain, but it was a lot of work.
It's farming.
Yeah. Farming for performance.
I actually am. This is one of the topics I'm super interested in, actually, which is like JIT type thing. And you know, I was telling you about the constraints that I'm looking at, and one of the factors is that the programs are quite small, and so I was thinking maybe I should just run the programs or in advance in a simulator and see what they do, and then feed that in as if I had a JIT, but I'm actually statically compiling. And I'm wondering if that's something that, you know,
it is a thing. Yeah, it is a thing.
I would have said that you just as much work to do an actual profiling and JIT in the middle, although you might have to walk away from closure as your JIT engine for being too slow.
You will fall in the category for the profile guided optimization. You run the program, you figure out it, and
well, so an idea that I had was to just compile, sort of like branch off at some pass level in the compiler, and then target the JVM. So target closure or target something and run natively. And because I'm like, you know, closure does the loops and stuff, I'll just strip out anything that's not relevant. I could just add instruction counts and basically run like a little program that's you know, just burns through. It doesn't really interpret, it's just running.
And then when it's running, the results that you're getting off of what you would have otherwise gotten off your AI chip, you're not actually interested in, you're going to throw away. And
yeah,
you're just looking at
all I care about is counts. Yeah.
Yeah. There's a Loris Ball paper from 30 years ago. It talks about optimizing your performance counts, but I don't know if that's, oh, here's Max Bernstein now under a whole other name. You got, okay, fine. Hey, Max, we were just taking your name in vain a minute ago, but we have a bunch of new people here talking about all kinds of fun hardware chip stuff. And I don't have any noise from you yet, so you're still muted, which is fine. All right, Derek, carry on.
Okay, well, yeah, so anyway, that's an idea. But so one of the questions that I have, this maybe sounds kind of stupid, but okay, so I kind of have an idea of how I can gather statistics, but I don't really have much idea what I can do with them. I mean, I have a general sense.
Okay, I can tell you what you can do with them. Yeah. So first thing is that there'll be places in the code where somebody wrote code that you never get to.
Yeah.
And then when it comes time to generate code for the chip, you can say, if I get to this code that I've never gotten to before, I want to stop, unwind, and go back to my simulation and try again. So you want to have a path that says, I'm running in some code on the chip. I hit a point where I don't know what the hell I'm supposed to do because I never got there before in my life. I want to stop and unwind, know the execution state of the world, go back to whatever my jitter is and say, please, sir, tell me a new way to handle JIT code or whatever, a new execution strategy forward that takes into account that we're now visiting this place that we never visited before. In the land of hotspot, Java, that was called a de-optimization. And we unwound from the running generated JITted code back to the interpreter, which meant we unwound from all your register allocations and all your instruction selections back to Java virtual machine architected state. And we ran in the interpreter a while, and you might have a different strategy than running in your interpreter. But we ran in the interpreter a while, and the interpreter reprofiled. And he said, and now I have profile stats in this area with code that you never went to. And then you went and rejitted. And in the beginning, when the program starts up, you hit a bunch of this stuff for a few times around. But after not very long, you rarely ran into code that you've never seen before unless you hit a major phase shift. And if you hit a major phase shift, you actually generally did want to rejit anyhow, because you're now doing something very different than you were before. So the strategy in your head is, how do I get from running machines execution state back to some sort of abstract IR thinking about that state, which I can then run forward in the interpreter or run forward in the abstract execution engine or profiler, and then get back to running again on the chip after I sort out what the hell I'm doing in the code that I've never got to. Otherwise, you're in lots of pieces of code that you have no stats on because you've never got to them yet.
Yeah, and yeah. So I think I have to think about this as more like male chess. Like it's like it's like you can have some good moves, but it costs a lot to go and send the take your turn and send it back to the other guy, because it's going to take weeks to get back. I mean, that's kind of how I feel would be.
The strategy that Hotspot looked at was, we can carry on in the interpreter at 1/10 the speed versus the JIT code. If we instead JIT code for places we've never been to before, because of the language semantics, we had difficulties. Like, there were things you weren't allowed to do. You had to do multi-threaded, cross-thread, Java class and init crappy games. It was horrific. It was better. It really was better to go to the interpreter. But also, if you carry on in the generated code without the profile data, you might be 50% or more slower indefinitely in the future versus stopping, taking 10 millis or 100 millis to rejet, and then going forward again. And then there's a strategy. You're looking at the cost of what's the JIT cost versus the go forward half speed cost. And there is where I say, you know, using LLVM or closure is like a painful way to rejet. But, you know, you want to get a first cut going before you worry about how fast your compiler is. But it does change that dividing line between carry on slowly, badly, and stop and rejet.
Yeah, okay.
After that, the things I used profiles for were lesser importance, and that would have been loop trip count. This loop typically tripped 0 to 1 was one strategy. You just unrolled it a couple times, and if it went more than that, you went to the unoptimized loop indefinitely, but you expected to peel 0 or 1. Or the loop tripped many times, and you hit it with every hammer you had. That was another strategy. There were often loops that were nested badly after people's inlining and strategies and if tests happened. They looked like were neatly nested in the source code, but they had cutouts left and right, and suddenly they were weirdly nested. And the outer loop had way more trips than the inner loop, which only rarely ever took. And you would have otherwise hotly optimized the inner loop. It turns out it was rarely run in practice, and the outer loop was where all the action was. So the profiles would tell you what loop to spend your efforts on and what loop to not care too much about. And it was helpful in the loops for sure.
The other thing to mention is that quite often the profile only tells you what you need to profile. So as you dive down one level, it just shines the light where you should be looking next. So that's one of the reasons why the hotspot model works, is because it doesn't just have one profile. It incrementally zooms in on the hot area. So by adding new profiles on each regen.
Right. So really the benefit is to run profile, maybe not try and get all the information. You do some quick run, you optimize, and then you see what needs to be optimized next. Is that a better strategy?
Yeah.
And that's something that could be done statically as well, right? I mean, sort of like alternate between.
Yeah, it can be done statically.
So I kind of think that
with a static profiler, but you're not going to get as much.
So sorry. One of the weird things about what we're doing is that oftentimes the controller programs get no input from the outside world at all. They're really given a job to do, and data is going to flow through them. And nobody's ever going to tell them anything except the data's here, the data's there. I'm ready to receive my stuff.
If the controller has no loops.
It has a lot of loops because it's counting, it's doing all sorts of.
It has if branches as well.
Yeah.
Okay, suppose those if branches and those loops have biases where they heavily biased left or right, or heavily trip count or short trip count. Now you can make optimizations based on that. It's already sufficient for the controller should be profiling itself. And you're suggesting doing that in your simulator, which is a fine way to get profiles. The hack I was going to tell you next here is that generating JITted code where you profile lets you get profiles at a hugely faster rate than almost any other strategy, especially including the simulator on the x86. So it's a strategy of JIT once with low effort at optimization and profiles counters put in using some reasonable, like the Loris Ball paper I mentioned, strategy. Run it for a while, however long that is. You get profile data really fast. While you're running this code and gathering the profiles, you go off and work on a better version of the JITted code that takes into account the profiles you're looking at. Then you swap out, and that means you stop the running guy and say, stop doing what you're doing and start again, exactly the same point in time, but in the new JITted code. Yeah. And that's the same as that DOP thing I was talking about before. It's the same strategy. You're looking at cut points in the generated code, once per loop, once per function, however you want to slice and dice it. where you stop and ask the question, is there a better method for me? If there's a better JITted code, if there is, it will be at this point, this execution machine state, program execution state point, and I will simply call over here instead of calling over there, and then I will take this code and unload it from my core CPU and throw it away and go run this code. And it will pick off where I left off, but with different generated code that takes into account the profiles that have been seen so far.
Yeah, it's interesting. You know, it's funny because I had been assuming that that would be something I don't do, but now that you're describing it, I don't see why we wouldn't.
I claim it's absolutely the way to go if you're looking at, you know, I mean, you got hardware, your entire schmick, your business model is we can do machine learning faster than anyone else. So time just has to be of the essence in your business model. And I don't know, you got your business model, you got a business model, but you just have to have time as part of your equation for your goodness that you're selling clients, which means if you're not, you know, saturating that chip and beating the hell out of PyTorch or whatever the fuck your competition is, you're going to lose. So speed is an issue. And now how do you get there?
Yeah.
And then you swap off engineering time to build it versus time to go run it. But there's definitely an interesting game to be had by collecting profile data, and then how do you collect them? And I claim the easiest way that I've ever seen to do it was to JIT it once. You're already going to JIT. If you already decided you're going to JIT it once with profile data, and then be prepared to swap out what you JITted for a JIT it twice. And then, you know, when you have these swap it out and go again strategy working, you can now give up compiling shit that you don't want to deal with, that hasn't happened yet and you don't like. This is really hard to compile. I don't want to deal with it. I don't care. You just cut off and say, I go back to my plan B strategy, which is stupid and slow, but it never happens. So I don't care that I'm stupid and slow when the never happen things happens.
Right, right. And in fact, if it's something you really think it will never happen, instead of cutting it out, I guess you'd send a message to the host and halt.
Yeah, right. Yeah. There are plenty of that. I had to do the Java semantics all the way, so I really would go to the interpreter. But there are plenty of times where I knew if you're throwing array index out of bounds exception, no one's going to catch it. The program just ends right here. There's nothing else going on. So take your cheapest possible bailout, whatever that was. Yeah, go to the host and say, I'm dead now. All right.
Am I audible now?
Oh, yes.
I am?
Yes.
Yeah.
Oh, great news. Okay. Hi, Derek. I was called in by Cameron because I heard there was another Python compiler person.
Oh, yeah.
Well,
so
sort
is
of.
that why my name was being maligned?
Yeah.
Well, I found your blog and there's already, I saw some interesting looking stuff, so I'm going to have some reading to do later on. But yeah, I mean, to call what I'm doing a Python compiler is, I mean, it is because that's my source language, but I'm targeting only a subset. And basically what I have in Python is about 10 lines of code that turns the Python AST into a bunch of tuples and then sends them to Clojure. And then I start compiling it from there. And so I start with a source-to-source compiler from Python to Clojure. And then from there, it's like a subset of Clojure as well, because I'm compiling for our very small risk controllers that only care about, you know, integer math and doing loops and conditionals and coordinating data and you know, running as efficiently as possible a big array of SIMD work.
Why do you go through Clojure?
Well, I started with Clojure as my language. I started with Clojure was my target language, and I got a bunch of horrified looks from people in the company.
People don't like
you know, we can't handle that many parentheses, and we don't have nearly enough commas. So, so I just did a source-to-source from Python to Clojure, and now everybody's very happy.
And so, have you looked at like Numba?
Numba? No.
Search Python Numba, NUMBA.
Yeah, what is it?
It's a Python JIT for numerics.
Okay.
There's another one as well that I can't remember.
So Max, what's kind of cool is it looks like he's kind of chewing out the hard parts that Python can't handle fast, like what Python usually does with FFI. And then he's sticking that down on the hardware. So it's to do the heavy AI crunching on the hardware, if I understand correctly. And then the rest of the Python just can run up in user space.
Well, it's really a little bit different. What I'm doing is I'm just using it as a, right now it's like a low-level language to write arbitrary programs for our system. Eventually, I would like to, you know, say, take a NumPy instruction and compile that to run some higher level program that may run on one or more banks on our system, or, you know, of course, neural net frameworks. But right now it's really like, oh, there's a loop. That loop is going to run in our chip. There's a, you know, a counter, or there's a conditional. And then here's a bunch of commands that mean nothing in Python, but when you run them on our chip, they'll run our SIMD array. And those look like a Python library. So, but yeah, so that sort of may end up being a library which emulates our hardware. So then you can actually just run in Python, and it would be, you know, pretty slow because the hardware is doing all this stuff natively. But, you know, you could actually get insights into what the hardware is doing when you do different calls, and you know, have autocomplete in Python and stuff like that.
In case you were unfamiliar, the term for that is intrinsics.
Yeah. So it's a bit, I mean, we have intrinsics, but this is a little bit, I mean, maybe they are still intrinsics, but they're fairly high level intrinsics, I guess.
But that's fine. I mean, APL, every other character was its own unique intrinsic for doing array math. And I'm serious, for APL, it was character by character. It's pretty ugly. But yeah, it's all intrinsics for doing array math.
I mean, yeah. My co-founder has been asking me, why don't we just use APL? Like,
oh, I see. I know I wouldn't recommend using APL directly anymore. You have trouble finding people who code APL.
Yeah.
You need a language to write your machine learning.
I mean, that's basically what NumPy is, right? It's like APL with more characters.
Yeah, maybe. Yeah.
Sort of.
I think so. I hadn't been thinking about it, but yeah, probably. All right.
You're perfectly happy to let the programmer decide what things they want to use the special hardware for? You don't need the compiler to figure that out?
Yeah, exactly. So I was thinking that just like annotating functions.
Well, the usual
whatever you call those things with a little @sign decorator thing.
Yeah. But you've got intrinsics, then you call a funny thing that said I called, you know, my language dot dot math dot whatever, and that was where it said switch to the hardware.
Yeah. So I mean, there's you could kind of figure it out, but you know, I was thinking that, you know, so for instance, we have special registers that are inside the PE array, right? So nothing accessible by the controller, but you still tell it what register to use and stuff. So, you know, there's a kind of intrinsic to say, allocate me one of these registers, or allocate me a variable, which becomes allocate this register. So the only way to support that in Python would be to have like an emulator of our chip.
So the question for you then is, what is the API you're exposing to the end user of your chip? And there's one API that says, I have very simplistic math routines that say, here's all the arguments, like the sigma cutoff value where I say this neural net element fires or doesn't or whatever as part of the API, and the user has no clue about registers on the chip. There's another API that says the user's doing register allocation because there's only a finite number. He's going to do it himself and tell you which ones to use. There's another one that says,
I want to avoid letting the users like try and have to worry about. It's allocating registers is hard.
Yes.
If you have to do it yourself. So but I need to be able to say, well, so what I want to enable is for people to write low-level, high-performance code on our chip, and they just happen to be writing it in Python.
It really sounds like you're pitching Numba.
I'm looking at Numba, and yeah.
Numba has got NumPy integration. It does broadcast. It does parallelism. It'll vectorize your shit.
A link.
Yeah.
A link would be.
Yeah.
Sorry.
Yeah. Just
I'll stick it in the document here.
And
if you can match their API, any code that was built to run it, it's now code for your chip, right?
Well,
yeah. I believe it's perfectly fine in your language to expose the primitive as a keywords in your language and expose a library with its function, which will be translated to your chip. That's most.
Yeah. So what I did is, where I needed keywords and stuff, I just did with bindings in Python. So, you can kind of work around the lack of macros or whatever, and it's a little bit more cumbersome, but it's not too bad. So, and I just convert it, and when I'm doing my source to source, I convert those into my own closure macros and then compile those. Or they look like closure macros.
Generic warning: if you define a language for yourself that you're the only person writing, and it's crucial to the company, then you rapidly become the expert. And if it takes off, you're stuck in that job, and no one wants to learn your crappy, weird language that only you understand.
You should target.
Maybe you won't fall down that rat hole, but just beware.
You should target some kind of a common API in order to ease the what are we trying to do, what are we targeting, and in your language we can go as low level as you want.
Yeah, that's what I didn't know. What API is popular right now for array math in Python?
NumPy.
Yeah, but this NumPy thing looks like it basically takes NumPy as its starting point, right?
I mean, you can write others. I think you can use other data structures, but it happens to support all the broadcast stuff natively.
Yeah, oh, that's cool. I'll look at that for sure. This is one level higher than what we need. So I think that we still need, what I'm building in order to build the primitives that this thing would need to use. And that's kind of what I was talking about before when I was talking about layers. You need
you have to
kind of a language to express the higher level stuff and turn it into functions rather than, I don't think I'm gonna be able to convince Numba to generate code for a chip.
They use LVM,
Probably.
So you would add an LVM backend and then.
Yeah. So I've heard many people mention the idea of creating LLVM backends, but I've rarely seen people successfully do that in practice. So it seems like
the Julia group
has a big job.
It's a big job. The Julia group has a reasonable backend, but they have no profiling, and they're using a JIT, and it's extremely slow as a JIT. Arthur, who's been on the call, he's not currently on the call, he was on the call earlier, has been doing it for Java. And again, the issue is, as a JIT, it's 100 times slower than the hotspot JIT. As a code generator, the code quality is only modestly better than the hotspot JITted code, and it's a lot of work. So you can get good code, it's slow, and it's also a pile of work. But so
you're talking about using LLVM.
LLVM as a code generator for anything other than what it's geared for, which is static compilation, where you're basically converting, convert your Python to C instead of closure and then hand it to LLVM. That's the path it's geared for. That's not so bad.
Yeah. So that's an option that I have looked at a little bit, as well as compiling to LLIR, whatever they call it. Their IR.
Yeah.
So just I could sort of if I'm doing multiple dialects, then that could be one. I could send it into LLVM for free work and then come back potentially. But it seemed very complicated, and
so basically your part of the language would become the front end. How it translates to an LLVM will be where the thing.
I mean, that's possibility to be the front end, to also be the back end. I mean, one of the first exercises I did, I went through our entire assembly language and sort of built like a data of like everything about every assembly call, like given a set of parameters, what is its behavior, so that I can try and make use of that later. But I think, maybe I end up being the back end. Maybe there's just some middle layers at LLVM, but I don't know. Like LLVM, to me, it's a big black box, and if I rely on it, I just have to rely on the big magic box doing the magic thing just so, and otherwise I don't know what to do. And I kind of, at this point, I'm thinking, okay, I'm going to build everything, and if I get stuck or something is just so hard, then maybe I'll use the magic box.
LLVM suffers from the first bite syndrome, which is to get the first bite in your mouth has to be the size of Texas. But then once you get the first bite in, you should be good, right? In theory. Max is laughing. I don't know.
Yeah, but most people want to bite off everything that comes with LLVM because it understands things about the x86 processor that would take decades to learn. Whereas his goal isn't, I need its deep expertise in x86 performance optimization, because that's not the chip he's targeting.
That's right. Yeah, we're a bit different. So if it does things that are good for x86 but bad for us, then I'm also undoing.
It targets mini chips. It has tons of generic optimizations, but I'm actually with Cameron here. Your mouth has to be the size of Texas to take that first bite. So the first bite's a doozy, and it takes a long time to get to where you eat the bite. And then, then things happen. It's okay. I'm kind of actually encouraging you to go down something related to the path you're doing. Take your bites small and manageable, understand what the hell's going on, and then make your call blow by blow. I'm going to live with closure for a while because I got it going, and then I'm going to decide to JIT twice or not, or whatever you're going to do. But I wouldn't grab LLVM, just know that it's out there and does a good job once you can get past that big haul first step.
Yeah. No, I mean, we've got an LLVM compiler. So the first measure that is going to be like, how do I compare it to the LLVM generated code? Right. And so,
You'll be a while, and don't go down you'll have to go down the register allocation rat hole, and I wouldn't recommend it as a first cut.
Yeah, well, I've got my move biased coloring allocator working.
Okay, excellent. So, shit, I have, the hotspot, if I can find this paper, it's really old. I did a bunch of work, obviously, on graph calling register allocators for Java. Well, in general, long before Java, and I have a way to do graph calling register allocation that's like 10 times faster without any code quality change than everyone else. And I couldn't get it published eons ago because everyone demanded I compare and contrast to linear scan. Of course, I produced better answers than linear scan. Of course, I was slower than linear scan, even though I was faster than everyone else who doing graph coloring. So the paper never got accepted, and it sucked. And so I got mad, and I quit trying to screw around with selling the paper. But honestly, there is a good way to do graph crawling register allocators. Let me see if this is a suitable paper. Here is a really old paper that does the actual key. Oh no, it's too short. God damn it. Where is the longer one? Sorry. Keep going. I'm gonna hunt papers for a second here.
The other thing I'll pitch another project. Derek, it looks like you muted. Also, is pure Python compiler infrastructure is this guy's project to have every single step of like a C compiler pipeline in Python. So you could do that in Python, like pure Python, add a backend. It's pretty easy to add a backend, and then you get, you could do that as well.
Yeah. I mean, that's kind of what I did with this course, actually. And so I guess you were in here when I was talking about this. I'm actually going to put a link to this. The course comes with a book, which is pre-publication. So you have to compile it yourself from LaTeX. But
compile a book? Sounds great.
Yeah. That's a compiler, of course. So start with compiling the book. So it's here. So this is
And
the
good
book.
news is if you find a compiler bug while compiling the book, Donald Knuth will send you money.
That's right. Oh, sorry, thanks for linkifying. Yeah, so there's a chapter, it's like chapter 4 on the register allocator. So I basically implemented pretty close to what they described there. And then that one doesn't do loops. And then a few chapters later, it's okay, here's how you add to it. So, you know, this is beginner stuff, but, you know, might be interesting. And I'm looking forward to your book, your paper. Definitely look at that. And so
okay. I put a really old version of it in the docs. I don't have an easy, shorter one. The main schmick I did was I pre-colored registers according to if they had a binding that was requiring a specific register, which is always true for calling conventions. Most interference graphs then had pre-colors all set up, and you would have too many conflicts because somebody returned a result in RAX and had to pass it in RBX. And so then you split live ranges, at the def and use site and win again. And there was a couple other hacks in there that aren't in that paper that I need to find. I swear I wrote up on how to do the coloring cheaply. The main hack was that I built 2 different versions of the interference graph, and you waffled every round through the allocator. You flip back and forth between them, and the one where you're doing the pull things out of the interference graph that have low enough neighboring counts that they are colorable, they're trivially colorable. That version has all your neighbors as a list. So you're an array. So any one interference is an array of a length of in-use neighbors, and the list of neighbors is just numbers. And so that's a 2D array, a ragged on the right. And then when you went to the 2D array and you found the guy whose neighbor count was below your threshold, you could pull him, claim he's going to be colorable, go to each of his neighbors, pull him out of pull the guy who's colorable out of their list, which made their list shrink. But their list is basically a Java array list or classic doubling array. You pull an element out of the middle, you put the colored guy on the end of the array, and you lowered the array count. So when you were done and you got everyone pulled out, what you had effectively was the list of elements that could be colored in the reverse orders in those arrays, and you unwound by just reinserting people, and you just add their length by 1, brought back in the next neighbor who's now trivially colorable in reverse. So it was a data structure hack that let you color it down and then uncolor it or put it back sort of very simply and quickly. That was part of the faster schmick. The other thing that comes around is that after one round of coloring, after that first round of coloring, the average color neighbor count was always 1 more than the amount of registers you had available, because you ran it up to the edge of coloring and then you failed. That's why you're doing another round. And most people are one-off being trivially colorable. So the heuristics that say screw around a little bit to go make somebody who's one-off actually colorable actually work, because everyone's almost colorable, or you would have spilled them already. And then of course spilling is you just chopped all the live ranges up and made a bunch of little live ranges and big ones. The other thing I did there was I made stack slots colorable. There's an infinite number of them, but it meant that your stack consumption for a colored code where you had to spill was actually very modest, because you colored the stack because you're already coloring everything else. Why not color the stack too? It didn't cost you anything. And of course you had an infinite number, so you never ran out of those. And then a spill was actually a move from a register to the stack, or stack to the register, and that was how it was expressed in the allocator. Anyhow, it was more about that. We can go down that rabbit hole a long ways, but there's ways to make graph calling allocators much, much faster than the sort of paper book things you might otherwise see.
Is that stack the call stack, or is that stack a separate stack for register spilling?
during allocation, I just kept count of how many slots I was going to need. When I built the stack frame, I went, I asked the register allocator, how many registers do you need? Plus there's some layout for passed arguments for, arguments passed on stack instead. Those are actually all run together. Now that I think about it, they were all run together.
I think Aaron's question though was whether you had a separate call stack structure from the actual stack structure. And Aaron, at the level he was working at, I don't think there's a separate stack. It's just the stack.
Yeah, it was the same
he
stack.
just made the stack frame slightly larger so you could spill.
Yeah. But the allocator knew here are arguments that were passed in on the stack instead of in registers because I ran out of registers. So the register allocator started with these arguments on the stack. Because stacks are registers, he just gave him a virtual stack register number. He has infinite number of virtual stack registers, but he colored from there.
Yeah. I think that's what I'm doing actually. Like I'm
okay.
So I have like the colors are just numbers, and I want to keep it under 14 or whatever is my number of registers that I can use, and then. But if it goes higher, then those just are stack. But it's the same algo no matter how high your number goes. Yeah,
right. And then the cost to moving a value from one register class to another is the cost of load or store, basically.
Yeah. But I was thinking that if I'm doing that, then with the register sharing, then I can just basically say, okay, what version of the register stack do I want to use? Do I want to use like 14 simple registers, or do I want to say 28 register halves? Or
drop the pairing on the stack, but know the size of the value, so that the register number increases however it does, but you used half or double sized elements on the stack.
Yeah.
And then renumber them at the end to pack. When all else is said and done, you don't care anymore. You can pack the alternate pairs,
Yeah.
But that's a later thing.
Yeah.
Pairing in registers requires you to add a bunch of interferences for the pairs to make that work, and you don't want to deal with that on the stack because no one fucking cares.
Right. Yeah, of course. Well, actually, one question was if I'm spilling a register pair, like would it make sense to spill registers in pairs if I'm, so that I can load up 4 registers at once with one read if they have, maybe they'll be useful or maybe not, but there they are.
Right. When I was doing that, I said the spill dropped them all, and the allocator now knew he had them both in a register and in the stack, all of them. And that the next time he needed to do something like he needed this register that had all, he whacked, then he took that register back and was able to use it for the next guy, but he had all those spill guys on the stack. And then the next time those got used, he pulled them off the +0 to +3 offset. He knew where they were on the stack.
Yeah.
Okay. Yeah, you spilled all of them, the whole pair at the same time. Now, on the weird thing is the x86, I was doing this with long math on a 32-bit register machine, so I need register pairs. It was actual register pairs. So I was spilling highs and low halves, and and it wasn't one spill got me 2, it was one spill got me half of 1, and I had paired my 7 registers, x86, so the earlier kind. You only had 8 registers. One was the stack pointer, had 7 registers. So I got 3 long math pairs, right? And so AXBX, CXDX, whatever, EI, SI, whatever, fine, DS, SI, whatever, fine. The pairs were there, and then it made for some ugly code. But I had it all working, and then we all went to 16 or 32-bit registers, and they're like, it's got some.
Well, the best thing about code is throwing it away.
Yes.
Absolutely. I noticed you didn't mention AL versus AH.
No, I never did those pairs. Never. Bad. There were some specially generated, like GNU super optimizer. This sequence computes the pop count before the pop count instruction existed. Crappy things that use those kind of things.
Yep.
But never. I know register allocators who did it. I mean, it would happen, but I was not in that space. But I did do 16 to 32. in bad old days. Oh, remember the good old days? Yes, but then there's some bad old days too. So, you know, there you go. That was one of them. All right, what else? We let Max go back to his coding days.
I don't know if you all are under the impression that I do work, but I don't. I'm just kept around. I don't. For the record, my official title at my workplace is Chief Potato. So I'm kept around for just my spudly opinions.
So it's some you deal with potatoes?
Well, I don't deal with potatoes. I am responsible for the direction and the vision of potatoes in our org, in our company.
Oh, it must be a big factory.
But potato is more of an attitude than a tuber in this case.
Yeah. This is a very Dilbert conversation.
This is a, sorry?
Very Dilbert conversation.
I mean, Dilbert's, there's been some stuff there lately, but this is a serious thing. If you go on Workday, it'll be like Max, Chief Potato. And actually, there's some fun stuff. Like some of the pages are gated based on your title. So some of them are like, if you have Chief in the title.
Yeah. But wait, you can pick your own title.
Yes, it gets to get approved, but mine got approved. So that's that.
Yeah, your manager influences your title picking ability.
Yeah. My manager was like, oh, that's hilarious. Actually, what happened was my sister called. She was working on a school project and she had to interview some people. And she was like, all right, what do you do? What's your title? It's like, look, my title's software engineer, but it could be anything. I'll just change it. And I went and changed it, and that was that. I've been Chief Potato ever since.
Hey, as long as you made it to the C-level suite, like.
I did.
That's what I was thinking. All right.
I don't have my own PA, though. Need an assistant to manage my really.
Going?
How is my project going? It's going pretty well. We're doing a version upgrade, though, because we're in Python 3.8. And people are hemming and hawing about Python 3.10. And that's annoying because we have to upgrade everything. But then that's probably the last full fork upgrade we'll ever do, because we're moving to be a C extension. So you could just install Cinder instead. And then you can like register your code with it, or like switch out your frame evaluator, and then it'll just JIT your functions. And that'll be that. And then we don't have to manage like, I don't know, 100,000 lines of, how many lines is it?
But you start with bytecode that comes out of the back of Python, or are you actually like parsing Python syntax?
We start with the AST. Okay. About 2 years ago, we were like, all right, we told this guy, Dino, you're gonna write the CPython compiler, which is written in C, in Python, but you have a starting point because there's this guy, Paul, I don't remember his last name, out in the world somewhere, who'd upgraded the old Python compiler in Python from 2.7 to 3.5. 3.6 had some weird changes. But we're like, all right, Dino, get it to 3.6, then 3.7, then 3.8. So Dino got it to 3.8 over time, and then we switched to that, and then we also based our other compiler, which is like a typed Python, on top of that. So we have our own bytecode compiler, and we can do stuff in there. So we do take bytecode. You could also, which means you could also switch out your compiler for our compiler. We don't do anything interesting in the normal Python compiler, just the typed one. It's got like an abstract interpreter to do like, you can't have side effects in the top level of the module, and that's really nice for like, if you have a bazillion lines of code, you don't want one module making a network request when you load it.
And you're inferring all those types. You're not getting them from the programmer, right?
Well, let me tell you, 4 or 5 years ago, no, it's got to be longer than that. 6 years ago, this guy, Carl Meyer, who's from Django fame, wrote this thing called monkey type, which takes all the runtime types and turns them into static types. And that was how we typed the whole code base. I think, I'm pretty sure this predates me. I was still in school. And So we have types on this enormous corpus. They're not perfect and it's not sound, right? You can still say like ignore, and then the type could be anything, and the type checker will just not complain. There's a type checker called Pyre, which is used for like correctness things, and then there's our type checker, which is used for type directed compilation, and that one you can't ignore on that one. So when we're porting something to our type checker, you have to go like nudge the types a tiny bit, and then it generally works. But so we have types largely.
Do you ever
Sometimes they're like any
type nudges and go back into the corpus with them?
Yeah, we do. We update the big code base. You have to.
Okay.
But and then sometimes you're like, okay, well, actually, this thing could just be a primitive int, so I guess we'll just use i32. Fine, and then that's actually unboxed right on the object, which is nice. But yeah, maybe you could use our static Python as your front end.
Is it? Yeah, Cinder. Is it public? Did you say it was?
Well, yeah, it's also put a link.
Yeah, I'm using the AST node as well. I mean, I can show you the code for that. That's pretty simple.
Oh,
it's like 10 lines of code that walks the entire AST using the generic visitor. That whacks on a little immutable variable on every AST node called info, and then it basically makes a tuple of the type name, every property in the node, and then all the children. And then as that sort of post-walk traverses, it turns out that the entire AST node is now turned into one giant tuple. And then that looks a lot like a S expression, and into my S expression compiler it goes.
You've just marshaled it.
Pretty much.
That makes sense. Yeah, please put a link to the
10 lines of Python. So, and then, yeah. So that's the extent of my Python in my Python compiler.
Put it in the thing, in the doc.
Yeah, sure, yeah.
I mean, you could probably, so we do typed bytecode, which we then ingest in the JIT or run in the interpreter. But you could also probably write a C backend or some other backend that'd be pretty straightforward. And there's this other guy, Andy Chu, who's working on Oil Shell, and he's working on a Python to C++ compiler that he occasionally posts about. And that's a pretty neat project.
There's a lot of Pythons around here.
But there's like 17 guys doing Python to C floating around. Whatever happened to like PyPy?
Yes. PyPy exists, but our Python compiles to C, and actually that's one of the works. So I contacted Carl Friedrich and was like, okay, you two should talk. I love doing that. I love just reaching out to people and be like, you two need to talk. So thank you, Cameron. It's a great job. And they're going to look at porting. Basically, all he needs is, 20,000 lines of Python to compile to C++. It's not arbitrary Python. It's 20,000 lines that his shell is written in.
Gotcha.
And it's not a one-time translation. It's like but the code won't change much, and it's not very interesting in terms of like Python features that it uses. So he's looking at building his own custom translator. But our Python would work. I think you could also get Cython. That would work. The only thing that's with Cython is that it requires, and our Python is it requires booting the Python heap. Actually, sorry, our Python doesn't, but Cython requires booting the Python heap and runtime and stuff, which takes some time. It has to like load a site module and blah, 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 blah. Yeah, that's a whole thing. But it's totally viable to use that as well. Because it's got type annotations, it's got unboxed ints, it's got everything. And I mean, I've retargeted the Cython backend before. We had to do that for our old Python runtime to target a different C API, but so you could totally use Cython as well. A lot of people in this game.
Yeah.
Well, there's a lot of developers who love Python, and there's a lot of developers who don't particularly like slow code. So
yeah, exactly. So I stuck this code in here, but it pasted really poorly. I don't know how you guys.
You could make a GitHub gist.
that's a good idea.
I usually wait till some eager person leaps in and colorizes it for me while I'm like staring at it. It appears to be magic to me.
Yeah, okay. Well, it seems like things didn't indent quite right, so maybe it can be inferred.
Oh, I got indentation of mine. It's not out of control.
Okay.
Somebody's got 6 character indents. Oh, now
No, it is out of control. You just can't tell because it's Python.
Yeah, exactly. There's an if and then another if right below it. And yeah, I don't know why. It seems to have mixed tabs and spaces together. Yeah. And I just
sure enough, fine. Well, ignoring the indentation, and we'll read between lines. What were you trying to show here?
Oh, so I thought somebody said, "Oh, paste it in." So I pasted it in.
This is your short code for walking.
This is the entire
Yeah.
Python portion of the entire compiler. So it's basically just a generic visitor that's walking through. It grabs some position information, but otherwise it's just doing a simple walk.
And there's Py to magic. So there's your name of your language is magic.
Exactly. Yeah.
Yep. Okay. And there's your grabbing line number, column offsets, inline, in call, file name, source segment. Okay, fine. Yeah. I don't know what else comes out of the walk, but sure.
Yeah, nothing else really. Just like, AST node gives like the type already gives you most of what you need because the type will be if or loop or whatever. And then just there's a few fields. And it's a bit messy. A short program turns into a long structure, but then the first compiler pass turns it back into a short program. Off you go.
Do you have some example input and output here?
Yeah, actually I have.
Yeah, because Max, we saw that same pattern with the stuff that you linked a couple months back. How each phase would explode, and eventually it was kind of collapsing back toward assembly. I don't know if you still have that link as well.
I do. Let me paste it in the thing because if you want to make an explorer, let me tell you, it's pretty straightforward.
And helpful. Yeah.
And extremely helpful.
Yeah.
Like I had to, fight some people to build this, and then now everybody uses it daily, and they're like, wow.
Why did we do this before?
Yeah.
Yes. That was my pre.
Actually, let me do better link.
Who needs a debugger? Who needs a debugger when you have puts?
It's not a debugger. Like, it's mostly, I use it for perf. But who needs a visualizer when you have puts? Yeah.
I claim I used mine for both debugging and performance. It was some of both. And I fought the first one going into hotspot. Why do we need a web browser to show the internal guts? Well, boy, I became a convert really quick. And then I proudly extended, expanded, and beat on it.
I'm sorry about the big link.
I've never regretted the time invested in making a 2-string or whatever.
That better tooling, yeah, 2-string tooling, yes. Oh God, AA's full. First thing I do, you make a new class, new whatever. First thing you do, all right, beefy 2-string.
Every struct needs a render.
Yeah.
I always make it so that my render can be pasted back in and parsed, so that I can just, copy and paste and not have to mess around with stuff. I never really considered Google Docs when I was thinking about these things, so I'm having more troubles with pasting. But
you would think that the Google Docs people would have long ago said, and this code, this chunk of text is code, and please colorize and indent accordingly.
Yeah.
And instead, you got, you can pick a font, Roboto New. You got Courier New. There's a Roboto font.
Yeah, but there's no programmers at Google anymore, so who cares?
Yeah, exactly. Like,
they still interview people to code in a Google Doc for your interview. It's not like the live coding stuff that they normally do. They ask you to type in a Google Doc. And let me tell you also, we have this is internal drama, but I'm going to go with it anyway because nobody knows where I work. We have this document thing called Quip. It's made by Salesforce. It's phenomenal. I love it. You can have code blocks. They'll highlight okay, but it's really useful. And then now we're moving to Google Docs. and engineers are all upset about it
because there's no code quoting or whatever. Yeah, there's no code colorizing, and I'm like, I'm with you on that. What the hell, Google?
I wonder how hard it would be
to Markdown.
I wonder how hard it would be to create an extension that does that for you.
Let me go ask.
I mean,
Google.
it's been done, but like, what's the point of making this enormous switch if, like, I mean, okay, most people are not in. Well, actually, I don't know. There's a substantial portion of engineers.
Here's code, adding code blocks to Google Docs. Click on the add-on section, get add-ons, go to Google Marketplace, search for code blocks, install. What the hell?
It's someone else's JavaScript package.
Yeah, there are some third-party things for that.
What? Okay, well, wait, we have to toy now. Like, where the hell is the, why don't you know where you find the add-on section here?
I love getting RC in someone else's doc.
Extensions, get add-ons. Okay, fine. What the hell am I looking for? Code blocks. Comes up the first thing you say, code blocks.
I'm just gonna send you a link to an exe I need you to install.
Code blocks, exactly. I'm getting there.
WordPerfect.exe.
I have to log in again. Choosing the, okay, fine.
Can't say I ever tried to do code coloring in WordPerfect.
Oh God, I have to allow.
You have to have a parser for that to color perfect.
Okay.
You don't have to. You just, every time you see the word for, you highlight it red.
But what is it there? Yeah.
Okay.
Unless there's some context.
I assume for that second code block, colorizing his closure was reasonable.
Yeah.
All right.
It is closure too.
It's actually not. It's actually Python tuples. Oh, actually, no, it's closure because the commas are removed.
Are you telling me that WordPerfect runs on color monitors too?
I used to run it on a color monitor. That was my first text edit. Oh no, you know what? It was not WordPerfect. It was Coral something.
Oh, I did WordPerfect on a
Coral Right.
I did WordPerfect on a black and white, and then I moved to a color monitor with WordPerfect. I did that. Yeah.
I assume there's no AA updates because you've been out of town.
Nothing hugely exciting. I could do. I'm screwing with code format blocks. I mean, because it's time here. Also, go to lunch. Yeah. I'm doing overloads in the type system. I got how I like overloads out of Henry Milner. They seem to be. It let me do a little more than is necessary, and I'll probably tone down what I actually allow. But I think I can do like every possible useful thing with overloads. I had to go back to my flow types and add nested, basically call graph tracking of the choices versus must-haves. You get to alternate in a hierarchically nested way. I must have this and that because I'm merging them out at an if function, so I don't know which one I got, and then here I have an overload where I'm going to choose between left or right at type time which one sticks. And then within the I get to choose, I might again have I must have another left and right, and this can be recursively done. So I just got to that state last night, and I did one layer of that and got up until I had like a horrific code example where I said, oh, this is really stupid, but it should be allowed. And maybe I don't care to allow it, but if I do, I need to update, flow types. So I could throw you the horrific code example and you can agree that I'm being stupid and I should never allow this code. But if I allow the code, then I have to update the types. And the syntax just totally allows the code. So I'm just like, well, maybe.
Do you have a code browser or Explorer?
Okay.
Yeah.
I just know I'm just dumping. Here's some AA code. Here's code that is the pure lambda calculus version of AA. I added a syntax, which is it's on the code block a little bit down here, which is the ampersand square bracket, which says I have two functions. They're overloads. I'm going to infer which of the two overloads I'm going to get. So fx is an overload choice of a function which takes an x and ignores it and returns a 3, and a y which ignores and returns a string. And so does fy is also a pair of functions which ignore their inputs and return numbers. FZ picks randomly between them.
So what's the type of FZ would be interesting?
Yeah, well, it's the type of the choice. Exactly. Of functions which ignore their input and return an integer, or functions that ignore their input and return a string. Then I pass it.
At type checking time, it'll oscillate back and forth.
I'm sorry?
At type checking time, you'll have different types every run on the type checker, potentially.
Well, it'll be always the same. I'm not sure.
You will have to
know that you have a choice. At every use point, he makes independently a decision which of the FZ choices he's going to come to. So at the next call down, where I ask, is that string empty? He knows that FC must return a string. He doesn't know which one. He's going to get a function from Y to ABC or Z to def, but he knows that it's a function which ignores its argument and returns a string.
Oh, God.
Yeah, so I'm not claiming that this is sensible code. I'm claiming that once I added the ability to do overloads, I immediately went, well, how bad can it be? And then I got that one. Then I have one step worse. So let me go through the one step worse. And then you can argue that I shouldn't go here. This is bad. Why am I here, right? So this one says, oh, indentation's horrific again. Of course, code blocks has no clue what the hell I'm doing here. So there's a function which takes a predicate. Then fx is using a predicate to pick between a function which multiplies by 2 or multiplies by 3, multiplies an integer by 2 or an integer by 3. Or the overload says, I take a float and I multiply it by 2.3. And then I return a pair where I use fx once with an integer and once with a float. And he correctly types that with the Hindley-Milner version of things to being a function which passes in a 2 to the integer predicate, which means the predicate dictates whether you get a 4 or 6 back. So he knows the answer is some integer, but he doesn't know which one till the predicate appears. So that's the code you get. And then the other one is obviously a 2.1 times 2.3. And he totally gets that at typing time and says, you're whatever, 4.9 or whatever the hell that math comes out to. And the typer gets it. So I am shockingly far along in typing this shit, not claiming that it's useful other than I needed to have overloads if I was going to allow integer float math widening using ad hoc polymorphic overloads. And so I said, well, give me a type theoretical solution for overloads. And I looked at type classes on Haskell and I said, I can do something simpler and better. And I did this hack, which resolves nicely on Hindley-Milner, and I don't have enough precision for my flow types. But a little screwing around will give me my flow types. And then I'll have exact call graphs with overloads. And
is
now
your type checker total? Like, does it terminate?
Yeah.
Always?
Well, my current belief is yeah. And I believe I actually have a strong theoretical argument why it always terminates, and terminates relatively quickly. And this is exactly a spot where I might go exponential on myself, and then I might like shoot myself in the foot. So up until I did overloads, I was pretty clearly everything's monotonic, and then I put Hindley-Milner in a monotone analysis framework. And because it's monotone, and then it has a run downhill until you hit the typing strategy. And in practice, my trip count through my major work list algorithm loop terminates in time that's relatively proportional to the size of the input text, except on the case where I got from the interwebs that this makes Hindley-Milner go ballistic. And in that guy, because I have improved the standard Hindley-Milner with the memorization algorithm step, I'm like n squared instead of n cubed or something. So I might be theoretically n squared up until I do overloads. And then nested deep overloads might go exponential, and I'll have to go decide if I love myself or this is stupid and stop it now. So yeah, I believe
there's a chance you end up in like the Swift situation.
What's the Swift situation?
They had exponential type checking for some case where like it took multiple minutes to compile someone's code.
Yeah.
And then I think
if you have full number expression, like 2 times 3 times 5, etc., you know, if it's long enough and more complicated enough, then Swift will take like an exponential time on it, and it will eventually say, cannot compile expression, the numeric expression, too complicated.
Really?
Well, it didn't used to do that. It used to just take forever, and then someone complained and they added enough, like they added a timeout or recursion level or something.
Yeah. Yeah, Julia was running into this. The prior DB company I was working with was using incredibly generic type overloading in Julia, and they were having the same issue of exploding out infinite number of things at typing time.
Yeah.
So I claim that right now I don't have any bad test cases, and the overload resolution game I'm playing might go ballistic. If I were to chop out return analysis for the typing, I believe I can go to a point where I do, I want to say, a tree-like breakdown of your types where you have to be hierarchically equivalence relations nested within a tree shape for the types, and that will bring you back down to like linear pretty quick, and also be entirely useful as it's, you know, it's a reasonable place to go. Right now, I can totally detect return types as part of the overload resolution. I don't claim that's what I want to do. I'm just like sorting out, you know, what I can do before I maybe back off and say, yes, but do programmers want to try to infer their types by staring at the returns? It's not much easier to think about it in a forwards only direction. And if I can't, then I would claim ambiguous, I don't hate you, you have to rewrite your code. And then you don't get to do things like, yes, and based on the return type, it's this. So I can do it. I don't know if it's useful. Like I said, I went down the typing theory rat hole way, way too far. But I wanted some overloads. And now, so I did an easy hack. And the easy hack is so fucking easy. And maybe it's just the wrong hack, but it's easy. So I had to say,
a question about the overload. So can you overload like literals? Like, can you make an overload of the integer 2 and the floating point 2.3? Or is it just functions?
The Hindley-Milner needs structure from his point of view, and he's the guy doing overload resolution. An int is an int is an int. So he will claim ints and floats he can totally overload, but ints of 2 and ints of 3 he will not. So if you do int and float as just things you're going to do overloads with, yeah, totally.
Okay. So okay. Yeah.
So structure. So primitive atomics. So int, float. Those are actually my only guys. Structures and their fields, functions and their arguments and returns. This is what defines an overload type. I'll let you pick between overloads.
Well, here, I'll put an example in the code block. Like,
yeah. Hurt me now. Tell me I'm stupid because of this.
The question is whether you can do this.
Oh, I'm sorry. And no. I only pick between functions. You can have arbitrary expressions as long as they yield a function.
Okay, so you'd have to do like, you know, x to 2.3 and x to.
Yeah, put your curlies in. And yeah, I'll resolve that. Okay. This will be a function which ignores its arguments, returns an int or returns a float. And I'll resolve that according to the use site, whether you're going to use an int or use a float. Yeah.
Okay. So
you're claiming I don't actually need the function part. I can just resolve the two things according to the types. I could do that. That's a good point.
I feel like there's a reason C++ doesn't like return type overloading.
Yeah, there is. I went and looked at the commentary on the documentation. There's a couple people who talked about return type overloading. And the most common answer was because programmers don't have a fucking clue what it means. So, you know, it's horrific to look at and understand. But to Alan's point, I could get rid of the function requirement and, in fact, infer between 2.3 and 2 directly. Yeah.
Okay.
I have the hunch that with this use in more context, it will have to try too many times to try which type do you mean? Do you mean the int? Do you mean the float?
That's the exponential case going on here. If you nest these expressions deeply enough, I think I end up trying all combinations all the time. I have a lot of cutouts for don't retry until something changes usefully, but you know, those are all like constant.
In the end, you can just give up and you want to type the overloads.
I don't give up if that's what you're.
To ask the user to disambiguate the to annotate.
This is like what theoretically can I do? So and then if it goes exponential, but no one ever writes the exponential code, we're all happy and we walk away and we're done. If it turns out that it's easy to fall into an exponential rat hole, then I probably don't want to go there. Separately, there's the rat hole that says no one understands what the hell the code means, so don't go there anyhow because you're writing read-only code. And that's the one that don't do return type overloading.
Not to mention it can lead to a case because you don't have type annotations. It can change the code the compiler can figure out, but it doesn't necessarily mean what you
think. Yeah, that's the issue. Now it has to be unambiguous in the end. Mm-hmm. So in the end, there can be only one answer, and I'll tell you what the answer is. And of course, you can add annotations to tell you what you think it is, and then the compiler will complain that what he thought and what you thought are different. But it's still, if you end up doing inferencing,
most of the language, let's say, I believe, Scala disambiguates on the first argument to a function if it's overloaded.
Yeah. So does this pointer or the argument after this pointer?
In the first argument, that the functions accept. If you have x with an int and x with a float, it will be able to disambiguate.
Well, do you count this pointer as an argument?
I can.
That's the question. Like I could go there as well, and right now I do disambiguate because I do these functions based as a field lookup on the left-hand side argument, the first argument, the dis pointer. Mm-hmm. So that already gives you disambiguation on the first arg, and then now I have second and more args in the return, and I could ditch the return. I could also require that the extra args tile the typing space in a nested tree fashion, and there are no crossing boundary lines where int and float and int arguments cause you to get things that look like they partially cover the space or overlap and say that's not allowed either. Yeah. That kind of a modality would get you types that are, I think, very easy to tell which one you meant, and a little more restrictive. Whereas what I'm doing right now is I say, try the left, try the right, try 2.3, try 2. Do both of them work? You're not resolved yet. Keep going. Try them both. Only one works and one fails. Well, the fail guy will never ever succeed later in the typing algorithm. Having failed once, he will only ever fail. So now I have one. Take it. If that also fails, you have type error. If it doesn't fail and you only got one, you were unambiguous and away you went. And that's like trivial, right? But I visit that loop every time something changes near and around. And if I don't get a resolution, I have to visit again. And of course, during that visit, I go visit his members, which may themselves be overloaded functions nested however deep. That might get me to exponential. And that's the thing I'm like, no, twitchy on. So we'll see.
So does the code end up looking like a constraint solver? Do you use a constraint solver for this?
So you're talking about the typing system, or you're talking about what the syntax looks like? So I have two different syntaxes, and you're talking about typing. Constraint solver is a way to solve the types.
Yeah.
Okay.
I don't know. I'm just wondering.
I'm hoping that I have an efficient linear time algorithm up until the overloads here already, and I don't need a constraint solver, which won't be any faster than what I got. So up until overloads, I have a hard theoretical proof, not a proof I've written, a hard theoretical understanding that leads me to believe I have fast linear time. Except where Hindley-Milner itself blows up quadratically, then I'm size of the typed result. Linear in the size of the program's typed result, which might be quadratic for Hindley-Milner, the ugly case that no one uses except for as a counterexample. Right, the people who write Hindley-Milner write Haskell. They never run into that test. Fine.
Yeah.
So I claim I'm already as fast as theoretically reasonably possible. I don't need a constraint solver. If I go exponential here, I'd rather back off from being exponential than throw a constraint solver in.
Makes sense.
I want the program to be understandable at a glance and not typable with enormous effort, but understandable at a glance.
Yeah.
So the original design for this was to say, I have an operator plus, it has int plus int, float plus int, int plus float, float plus float. Now I'm not doing any widening operators by default. Instead, I'm picking one of the 4 different primitives which are going to widen internally or do what they do. But that means I do overload resolution based on your types to mimic what you get out of a C compiler, or at least let you write C-like code and have it typed the way you think it should, although it's actually flipping between multiple different primitives as opposed to changing a type of one of your arguments and then inferring after that. So Java and C both have this game where they said, I saw 2.3 plus 2, and I decided I'm going to widen the 2 to a float and then resolve you as a float addition. But that means he widened an argument and he called the primitive add. So all my primitives are themselves just user definable operator overloading user definable functions. How do I pick which one? When do I widen? When do I not? So I'm never widening an argument. Instead, I am overload resolving. That's the theory here.
Oh, before we leave, I wanted to ask people about constraint logic programming, which is my new favorite paradigm. So,
you like prologue or like?
Well, I mean, I'll give a 3-sentence summary. So the idea is you write down a bunch of constraints, you know, like x greater than or equal to 2, or, you know, y equals, you know, 3z plus 5, or, you know, whatever. Lots of constraints. And then you just feed them to a big constraint solver. And it's okay, the solution is x equals 2, y equals 3, you know, z equals 5, right? And then, you know, that's your solution. And so, you know, and that's your program, is you just write down a bunch of constraints and you solve them and you get an answer.
Yeah.
And so I was wondering, you know, like, you know, where does this fit into, you know, people's conceptions of programming languages? So they're like,
it's similar to, go ahead.
Okay.
I mean, like,
Go ahead, Kevin.
put it this way, do you want it in your programming language?
Yeah,
Like,
yeah, there is the practical implications of that. Idris has something called a type hose. You can leave the program type hole, and the Idris will try to synthesize a term that fits that type in order to guide you. The types guide you how you would write your program. And there's a bunch of languages that does this thing, and the backbone of this is constraint solving, SMT solving.
Sorry, Alan. I'll take a slightly humorous approach on this. There's a concept called defect-driven design, DDD. Anyone heard of it?
Say that again.
So basically,
defect-driven design.
You've heard of like test-driven design, right? TDD. Well, this is DDD. It's called defect-driven design. So you know, it's like I went into a client. The client said, "Well, this is what I'm looking for. I'm looking for an application. Like there'll be an icon on the desktop, you know, with the application when it's installed." So it's like, I come back the next day. You know, he was expecting it to take years. I come back the next day. I give him an installer. He runs the installer. There's an icon on the desktop. It's like, cool. I can't believe you got it done. He clicks on it and nothing happens. He's like, wait, this is supposed to launch an application. I'm like, okay, defect number 1. Icon does not launch application. Come back the next day. Give him the installer, he installs it, there's the icon, he launches it, and up comes a blank window. He's like, no, there should be, you know, and it's like, okay, defect number 2. And you know, once you get through all the defects, he has exactly what he wants.
This would never be called incremental design or incremental requirements or anything like that.
Well, it's
Is that the minimum viable product?
Yeah, exactly.
In most cases, yes.
Oh, I mean, it's a good way to program, right? You know, I mean,
it's called lazy programming.
As long as the guy's got money, it's
agile, right? That's the only true realization of agile development methodology. Customer requirements first.
Yeah. Well, I've tried using constraint solvers for projects before, and I've never kept them. I've gotten something working sometimes. Usually that's helped me figure out what type of imperative program to write, and I just write that, and it's way better. And often I can't even get anything working at all with a constraint solver. However, it's just one of those things that I find kind of interesting. And so someday I assume I'll find a way of using it in Anger.
This sounds like me with the GNU Super Optimizer. Every now and then, you know, the old hotspot days, I'd pull that thing out, write down the fucking constraint. It would just do the exponential search over all time and produce some wild and crazy answers. And you'd like, holy crap, you can do that? That's cool. And most of the time it was just like, yeah, I'm still running. I'll get back to the next millennia, you know.
Yeah. So what's the problem called with the generic constraint solver, the exponential?
Yeah.
What's it called?
SMT solving.
Yes, that's the one. That's a,
There's a problem called state
The one is
space.
SAT. The one is SAT, satisfiability.
Sat solver, satisfiability.
SAT solver.
that's-
the SMT is
the
the
one.
more powerful. Satisfiability model theory, something.
Yeah. So, I mean, the problem is called state space explosion, is that there are too many values for variables.
Yeah.
Drop for a few minutes and you got to linear programming.
Yeah,
As
that's
a
what you
matter
get
of
for
fact,
dropping out.
So I believe, Alan, there is use for this, but right now the tools aren't ripe enough to guide the programmer.
So if I
I
write
found out-
using constraint solver in a good programming language, it could be the next, big programming language.
Yeah.
I'm with Derek on this one. I've used them a few times and
Well, Alan,
interesting and helped me understand the problem, and I'm not writing my programs in them.
it's important to set your goals correctly, though, Alan. So, like, when you say successful, what you mean is more users than Idris, right? So, all you need is 5.
Excellent. That DB company I was working for last year was basically doing something similar. That they were doing, constraint resolution, not imperative but descriptive programming for database queries. I think I think the concept's reasonably sound there, and I think their implementation strategy sucked, and they didn't like my telling them change your strategy, and I didn't like working with their strategy, so we parted ways. Fine.
Well, I mean, I'll explain the reason I like logic programming suddenly is because, so overloading, you can represent it as non-determinative. So your overloading operator, it doesn't just choose things by type, it just non-deterministically picks one of the values.
Yeah. I mean, I got a nice incremental way of doing that up to a point, but if it's all non-deterministic, it does, I think it's going to go exponential.
Right. I think that once your types get complicated enough, it's easier to just run a program than to figure out the type.
Yeah,
So.
F star does absolutely this thing. It emits the Z3 solver format in order to figure out the types. I believe that was its doing. I believe this is designed part of the design space it was meant to do. It interacts with the Z3 solver to allow type inference.
F star?
F star.
F star. What is F star?
F star is a development programming language by Microsoft.
I thought they called it F sharp.
F star.
There's 2 different languages. There's F sharp and there's F star. F star is like a proof language that has dependent types and stuff like that.
All right. Okay. Yeah.
All right.
The obvious programming language for Microsoft should be F@.
Have you considered some intermediate choices like Datalog, for example? Because Datalog, that's a subset of Prolog, and with tabling you can make it terminating. It's only first order logic. You can solve typing in it, for example.
Isn't Datalog terminating but exponential?
Datalog, yeah.
That's where my overload solution probably goes. So I do have to back it off.
I feel like exponential is not actually that much better than an infinite loop.
Oh.
If it's exponential on corner cases and linear, this is the Julia problem, right? It's linear in what you might like to expect, but you can drive yourself in an exponential corner. Is that useful or not?
I mean, I can write an infinite loop in programming languages that are still useful.
No, so at typing time. So I come to the compiler, I say, please, Mr. Compiler, can you make something that'll run this code? And the compiler says, I have to type it. And he goes and he says, okay, I'm like Swift. 99% of the time, I'm done in a fraction of a second, and it's done. I've typed you, and then I've jitted code. I'm good. We're happy. We all run away. Every now and then, I take 20 minutes on some codes, right? The Julia folks can be run into a corner where all the time it's ugly. I don't want to go there. So now you guys have talked me into thinking I got to back off from this. And maybe if I back off, I don't need to upgrade my flow type precision. I need to downgrade the set of things I'm willing to overload.
You will have to find some way to pretty much restrict how the overloading would go.
Well, the obvious restriction is to claim that the place where you would nest types have to tile the space in, I would say, an equivalence relationship. And the act of tiling the space removes all crossing between argument mixings left and right. Immediately chops you to some linear thing.
Yeah.
The problem is that some of those potentially exponential algorithms are so freaking handy in terms of what they deliver you in the common case that crossing them out up front makes for some really ugly languages.
Well, okay, so give an example where having an exponential typing algorithm lets you write a type that you'd like to write. Where are you going?
We hit it all the time. We hit it all the time with lambdas because with lambdas you basically have a pipe where what's on the right side of it ends up shaping what comes out the left side of it, and nobody's specifying any types, and then they create a pipeline of lambdas. So lambda calling lambda calling lambda.
This is the Hindley-Milner solution, and it's not exponential. If I get rid of my overloads here, I just have back to the classic Hindley-Milner with whatever extensions I have. I am not exponential. But you can nest your lambdas however deep you want. The trick there is that the Hindley-Milner algorithm uses the Tarjan disjoint union set find operation to cause the equivalences between the types to be computable like in constant. That's basically, it says I can find my equivalences in constant time. And that removes any exponential blow up going on here. So maybe we can walk through that algorithm another time.
Does it really use union find? I've never seen that.
I use it all the freaking time.
No, I mean, I've never seen it used in Hindley-Milner. Like we used like a freaking hash table or something.
You go to Hindley-Milner and they say, I have to unify two things.
Yeah.
At the core of that unification, I have two leaves that need to become one leaf. They always use what is effectively union find. It is not directly union find, it is effectively union find. For all intents and purposes, including theoretical runtime, union find. So it's just, I take the leaf number one and I want to unify him with leaf number two. I pick one to be the victim. He points to the other guy. Every time I look at a leaf, I do a find, which rolls up all the nested I-22 and gets to the top of the tree, rolls that up, and then, along comes Tarjan to say that running time is in log n. And log is such a hardcore reduction that's effectively a constant. So you're just linear and it's done. And I've been doing that for a long time, and I've stared at these algorithms for a while. I could step you through that. I mean, wherever he says I have to unify, it's a structural breakdown, bang, 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 until he gets down to a leaf. Here I have a leaf. Here I have a complicated thing. Make the leaf.
Oh, yeah, there you go.
The same. That's a constant operation, which is essentially a union step in the union find algorithm.
In the next talk, we can step through it.
Yeah, okay, fine.
Next week would be good. I got to lunch soon. Apparently, so do you.
Yes.
Also, did you move? Your workstation's not by. You moved houses, or you just moved in the house?
I moved houses, so let's see if I can not break my cabling and everything else here. So out of my
you really moved? Holy shit!
I'm in the mountains above Los Gatos. I have a 10-mile view to the city of Los Gatos and Capitola, and 40 miles to Monterey Bay. Across the bay there, you can't see it in the camera resolution, I'm sure. I'm up in the mountains. I'm on, I got septic system and gas, and I'm the last house on the Comcast cable lines. I have good cable still. I can walk out my door onto a trail into the woods where there are the classic California big trees. Like within a half a mile of where I walk, there's a tree whose diameter at the base is probably, the radius of the base is probably like 50, the diameter is like 20 feet. At 10 feet off the ground, that thing's probably 15 feet through that tree. And the tree is probably 200 feet high, and that's half a mile from my driveway. come visit me in my new house out in Sunnyvale.
Very good bakeries.
And you know, come have a beer on the deck, and we'll take a walk through the woods. We have fox running across our lawn all the time now. There's like fox babies and pair of foxes and a baby fox. And deer, of course, come and, you know, eat the garden. And there's peacocks and coyotes and stuff.
Are you on 9 or 17?
I'm sorry. I'm on 17. I am go up 17 to Summit, like the very peak between Santa Cruz and Los Gatos. Very top is Summit Road. Take a left on Summit, go 10 miles, and then hit some twisty roads for another 2 miles, and you're at my house.
So you're between 9 and 17. Oh no, left.
No, other way.
Oh geez. So you're by demo.
By who? What?
The SoCal Demonstration Forest.
Yes, I can walk to the SoCal Demonstration Forest out of my driveway. Down the trail, the very trail talking about the big trees, that's heading into the SoCal Demonstration Forest. Yes.
All right. If I'm going to visit you, it's a 50-mile bike ride, which is my only mode of transportation to your house.
Get a car.
No.
I'll take a train and I'll pick you up from the train station and take you back.
That would work. All right. 50 miles. That's a nice ride, though.
Well,
I'm in Redwood City. We'll carpool when we go over to hang out with Cliff.
Okay. Come hang out on my deck.
Compiler Coffee Club. That'd be cool.
We can do that.
I got lost in your neighborhood once when I was driving a rental car from Santa Cruz, and the road was a giant traffic jam going back up to the valley.
Yes. And
so I was like, oh, I'll take side roads. And so I just went on side roads, and then there was a road closed. And so I was like, oh, well, I'm supposed to go right. I'll go left. I went left, and Google Maps took me around in a circle for an hour. And then it brought me back to the same place. And then I was like, oh, wait, I think this looks familiar. And so I decided to turn off Google Maps and go back to Santa Cruz, and then just join the traffic jam, which had cleared by then. So it was okay.
Yes. So when I first moved to the Valley like 25 years ago, I was trying to decide if I was going to live in Scotts Valley, have a cheaper, bigger house, and commute on 17 or not. So one day I decided to drive up 17 very early and then drive the commute, see how it was. Because 17 was gruesome. Of course, people drove bat out of hell because they're all commuters and they know the road. I was like, do I want to do this every day? So I got up really early and I listened to the radio, and they said, we have an overturned cement truck at the top of 17 and there's too much traffic. We can't get a cleanup crew up there. And I said, I'm not going to go. I'm going to wait a little bit longer here. And about half an hour, they said, well, the cement's all over the road and they can't clean it off. So they have to wait till it hardens and then take jackhammers to clear it. So if you have an alternative, take it and expect 3 hours delay. And I was like, there's my sign. Don't be on the wrong side of 17 when the traffic hits. So I lived in the Valley for 20 years, but now
17 is just objectively dangerous.
Yes.
Even without the cement.
Yeah. So I drive 17 periodically now. I have my high-end sports car. I'm all happy. I'm more semi-retired. I don't have to take the commute every day. I can take it off hours. It's all good.
It's so beautiful up there. It's nice driving around anyway. So
yeah, come visit me. And that one, it's literally, that's an open invite for everybody here. Send me an email and we'll schedule a time. If multiple people want to visit, then we can hash it out on the mailing list here or hash it out at the meeting. I don't care. And pick a date that I'm in town. And, come visit.
Cool.
Beer on the deck, wine on the deck. Right now I'm looking at raptors circling in thermals. They start below me and they thermal up until they get above me, and then they cross over my house to somewhere else and they come back in the evening. So pretty much every day I have 2 or 3 raptors orbiting below me up until they get above me, and then they head off. It's a nice life if you can get it. Yeah. All right. Well past Cliff bragging about his new house time. Yeah, let's call it. It was very fun today. A lot of new people, a lot of new stuff. And Matt Chernick, boy, you got to work on your public presentation and make it exciting. So I'm actually kind of curious what the hell you're doing. And we couldn't get a clean, just a
I'll have to think about my elevator pitch a little bit more.
Yeah. Give us the elevator pitch next week. I'm looking forward to it.
What are you pitching in 5 seconds?
That's I'm trying to that's what I'm trying to figure out.
Right. Okay.
I'm
so
new language, fast and simple is the goal.
Fast and
I
simple.
like it.
I was claiming that same for AA, except I went down the typing rat hole. So when I come out of the typing rat hole, I still claim I'm trying for fast and simple, but
is there a link?
It's in the chat. I guess you joined after flogram.dev.
Oh, Flogram. Nice.
Oh, it's in the docs or something. I went around. Yeah. Okay. Yeah, it's on the chat. Cool.
The trick to being fast is to make a lot of stuff not allowed, but the trick to getting adopted is to allow lots of stuff.
It's not fast. And then, JavaScript and Java and engineer the hell out of it to go fast. But don't pick the language features that can't be made to go fast.
Yep.
But then you have to pick all the rest, so people love you.
Then you'll end up with Ruby.
No, they pick language features that can't go fast.
Oh no, hold on. They picked some. It's not the language features, because you can do a lot of crazy stuff in Python and Ruby and still make it fast. It's just that people decided they really love to use those features with abandon repeatedly. So modifying types is fine every once in a while, but if you make it a core part of your application, it's excruciating.
Well, I would claim, but fine. Yeah, I'm not allowing you to modify types on the fly. That's not a thing.
Why not? You just invalidate your caches and refill them later.
I want to claim programmer understandability. Use a new type variable.
Oh, that's a separate thing. That is a different thing. That is orthogonal.
Cliff, I was under the impression. So what happens if I use eval and try to make a new thing?
You use eval and you made a new thing, but that's
like
not
I could totally modify types.
I would claim you made a new type. So Cameron has this theory that for every service, he closes it off and the type system is nailed down in that service. And I'm basically there. Your types are nailed down. Eval produces a new thing. The new thing can have a new type. Just like class for name in Java. I sucked in a new thing. It's got a new type. Okay, fine.
Okay.
But the old
so
stuff
I have
didn't
global
change.
mutable state. I just built a new type and assigned the old global name to the new type.
Nope.
In Cameron's case, no, right? I think in my case, I'm okay with that, because if you're assigning a thing to a global variable, I'll know that at typing time, and the type of that global variable will be very generic, very weak, because it's being assigned by the result of an eval.
Yeah, and remember, we have a class type difference, so there's a divide between classes and types in our design, which is, I think, unusual. Not that I'm very academically aware, but but to introduce a new class, you have to introduce a container, because the new container would have a type system that closes over the types of the type system has to be closed over, which is why you can't introduce a new class to an existing type system.
But you can make a new container.
Correct. Anyone can make a new container because there's no security problem with that.
Right. I'm actually looking hard at what you're doing there and see if there's lessons for me. But I think you got some good stuff going on there.
But we are actually exploring the concept of eval in a more controlled sense, not introducing a new type, but introducing a new function for handling what we used to call a lightweight container, for handling things like, well, we have 4 use cases: debugger eval, which is an obvious use case.
Yeah.
And since we're self-hosting everything eventually in terms of eating our own dog food in the language, we'll need that. So there's debugger eval, there's database query, so being able to take a database query and produce a function that represents the predicate as but one example.
Represent the type of the result that you got back from the database as a typed result.
Well, in this case, the result's a Boolean. So imagine I've got a columnar database. So indexes. If I do bitmap indexes. So I need a function that takes I don't know. So say you're designing for, say, AVX 512. So you got a 64 byte chunk of ones and zeros, and you want to return out you basically want to map 64 bytes to 64 bytes, where each bit represents one row in the database or one entity on the table, whatever you want to call it. So you need a function that for a given, let's just say, entity in the database returns a 1 or a 0.
You get a bit vector back, however that's done.
Right, bit vector. So
yeah,
so that's that's what we call a predicate.
Yeah, I was thinking, what if I connect to a database and I want to get like the schema of the database turned into a type system and then get records out of the database under that schema? Do I make a new?
I'll show you that one next week, and we do that completely differently because that's
within
the container. Yeah, so we create a container with a database schema as a type system, but we'll cover that some other time.
All right.
Lots of fun topics.
Has anyone ever called you performance cliff?
Performance cliff? I fall off myself all the time. No one has called me performance cliff, but I've done performance work all my life and been, I want to claim, extremely successful at it. Now,
I'm sorry, what was that, performance cliff?
Exactly. I'm trying to fall off by tripping on my own 2 feet here. Why did this come up?
I don't know. We were talking about performance and your name is Cliff. So
yes.
And then also we're talking about patterns that are hard to optimize.
Right. Good Burning Man name.
Oh God, don't bring computers to Burning Man.
I don't know about a nickname, but there's definitely a t-shirt joke in there somewhere.
Yeah.
If you're going to Burning Man, you'll run into my parents.
Oh, nice. Are they going this year?
Yeah, they're going.
So is Starlink still optional at Burning Man?
I'm sorry, is what optional? Pretty much everything's optional. I'm sorry, clothing, sanity, all it's optional.
I said Starlink.
Oh, yeah,
even
Starlink.
Typing.
Yeah. I think pretty much for past the days where people put up rogue cell towers to intercept all cell phones and steer you off to rat hole land. There's like proper coverage. Burning Man's giant flat area, as soon as you put a cell tower one on either side on those hills on your side, you got the whole valley covered and you're done. So there's proper cell phone coverage now. I certainly went when there wasn't, but fine. Good, bad, ugly. Yeah, so Max, ask your parents if they want to connect with me, and then I'm happy to go say hi, and we can connect or not, whatever.
I'll tell them if they see a weirdo with a goatee. That's you.
Yeah, thanks.
That may not be specific enough.
I realized that I was saying it. There's going to be hundreds. All right, I got to run.
What do you mean hundreds? Oh, fucking thousands, dude. What are you talking about?
Goatees?
Yeah.
Okay, I don't know. I've never been. Anyway, I got to run.
All right. Bye, everybody.
So Cameron has this whole containers thing for lightweight isolation.
Yes.
My assumption in AA was your plan for lightweight isolation was closures.
Yeah, strong types. And then that doesn't cover resource constraints well enough, which is one of the things you get out of Cameron's container styles, like in particular size of your heap and whether or not this particular container is allowed to consume all of memory and crush all of the containers under its out of memory footprint bug or not. And a stronger container relationship might let you launch containers whose resource consumption is unknown right now and risky, and then crush it before it gets out of control and say, you, sir, suck, I'm killing you now. And that in turn lets you run somebody else's code that is like crappier than hell in a resource constrained way. And one of my grand theories for AA was I wanted to do resource management at a typing system level. And maybe Cameron's solution's a better one. So I haven't beaten my head down that rat hole yet.
I mean, I guess you could fill the sys object with a bunch of special calls. Sys dot call this thing with a different environment so that it can't get out to the file system. Sys dot call this thing with an amount of gasoline. So if it runs for more than 10 seconds, kill it.
Yes, right. And there's something going on there that I haven't sorted out. So I don't have an answer of how to do that.
And we don't have a sys.
I'm sorry?
And we don't have a sys.
Yeah.
We don't have Aaron's sys.
With the extra Y's involved. Yeah.
Some magic thing that is just in your environment automatically that you didn't define.
Right. I haven't got there yet. So that's either a member of the type theory, or if I can't do resources in types, which maybe I can't, then I need to have some sort of container like boundary that says, here is, yeah, the amount of gas you get. Here is the file space view one I can do. That one's easier to do. File space view, there's some other things, environment view and the like. I can give you a private view of everybody's file system by default, and you know, private meaning trimmed to what the owner who launches you says, the caller who calls you says, this is what you get to see about the world. But by default, it's what I get to see. But then, you know, I can say, no, you get to see less than what I see. And then I'll call this risky guy with a view of the world that says he sees /temp with 1 gig and nothing else. And he can't look at /home/cook see.
Yeah, I've often wanted that kind of default of like, if I execute this binary with no special privileges given to it, that there's some database where it can put some persistent state, but it can't go arbitrarily read my file system.
Right, exactly, right. And people who, people who want to use some database for some persistent state usually have legacy code that needs some temp storage because they can just hold it in memory and objects and whatever. But I want to write it to disk. I don't want to read it back. If they have it persistent, you have another problem where you have to validate you're talking to the same guy again when he comes back around for the next go to go back to his persistent state. And that's a useful paradigm in a lot of folks as well. But it's another one.
The usual trick I've seen there is a game of, if the binary is signed, then you get a persistent state object that anyone else whose binary was signed by the same key can read.
Yeah, there's a key.
And if your binary is not signed, only other binaries with the same SHA-256 get to see the persistent state you dropped.
Yeah,
and
exactly.
if you changed 1 byte in the binary, sorry, you're a new thing. If you wanted to have continuity of identity, sign it. Like,
you have to sign it. Right. Yeah, you have to do a crypto thing, and everyone with the same key can go get at the same persistent. Right. And then I asked permission from the user uphill from whoever I am at, please kind of have some persistent storage that lasts indefinitely of this order of magnitude. And the guy above me can come along and say, you get 3 months, and then I start whacking you off or whatever, and that's what you get limited to. And this prevents cookies from whoever lifting gigabytes of my disk space to hold stupid cookies from people who want to do.
Yeah, our runtimes could give us a lot more interesting security than they do today.
Yeah. Yep. All right, sirs, ladies and gentlemen, till we meet again. Bye.
Okay. Bye.
Ciao.